What if you could actually see energy? I don't mean just a flash of light or the glow of something hot, but the potential for energy laid out all around us like a kind of invisible topographical map. Well, today, that's exactly what we're going to do. We're going to learn how to draw that map for the unseen world of electricity.
I mean, have you ever stopped to think about a lightning bolt? It's just a mind-boggling amount of power, a colossal release of energy. But where does it all come from? How is all that energy just stored up in what looks like empty air between a cloud and the ground?
Well, it turns out the answer is in an invisible electric field. It's a landscape of potential energy just waiting for a reason to be unleashed. So our mission today is to map that landscape, to make this invisible world visible.
Now, to really get a handle on energy in the electric world, we're going to start with something we all know a little better: gravity. Think about it like this. You know when you lift a heavy boulder up a hill, you're fighting against gravity the whole time, right? All that work, all that effort you put in, it gets stored as potential energy. Well, electricity works on the exact same principle. When you take two positive charges and force them together, pushing against their natural urge to repel each other, you are storing energy in the electric field. One's about mass and gravity, the other's about charge and the Coulomb force. But the idea, it's identical. So, let's put a name to it. Electrostatic potential energy is the energy a charge has simply because of where it is in an electric field. You can think of it as the total amount of work it took for you to grab that charge from some far-off place where it felt nothing, physicists call this infinity, and drag it kicking and screaming all the way to its current spot. Okay, that's great for talking about the energy of one specific charge we've placed somewhere. But what about the field itself? Is there a way to talk about this energy landscape that just exists in space, whether or not we drop a charge into it? Can we actually make a map?
Oh yeah, the answer is yes, absolutely. And the tool we're going to use is the single most important idea in this whole explainer. Let's create that energy map.
And this is it. This is the crucial idea. It's called electrostatic potential, and we use the letter V for it. We take the potential energy and we just divide by the charge. Now, why do that? Because by doing that, we create a number that doesn't depend on whatever little test charge we're using. It becomes a property of space itself. It is the energy map. It tells you at any point in space how much energy a single little unit of positive charge would have if you put it right there.
In the unit we use to measure this potential map, you've definitely heard of it. It's the volt. It's named in honor of Alessandro Volta, the Italian physicist who gave us the very first electric battery. So yeah, next time you see 9 volts on a battery, you now know you're looking at a direct measurement of this energy map. Okay, so we've got a way to describe this energy map. Now let's see how these maps are actually built by the charges themselves. We'll start simple and then build our way up. For a single Lonely point charge, the energy map is pretty simple. It basically looks like a hill. See that blue line? That's the potential. It's super high right next to the charge, and then it just gently slopes down as you get farther away. But now look at the force, the electric field itself, in black. It drops off like a cliff. It gets weak way faster than the potential does. And that difference is really important for how charges interact over long distances.
So that's the map for just one charge. But let's be real, the universe is full of charges. So what happens when you start adding more into the mix?
And here, physics gives us this beautiful, almost too simple rule. It's called the superposition principle. All it means is that to find the total potential at any point, you just figure out the potential from each charge by itself, and then you just add them all up. That's it. A positive charge makes a potential hill, a negative one makes a valley, and the final landscape is just the sum of all those hills and valleys. You can really see this principle in action right here. On the left, a single charge's potential just kind of falls off gradually. But on the right, you have a dipole, a positive hill right next to a negative valley, and something really cool happens. From far away, they start to cancel each other out. The overall effect is that their combined energy map flattens out way, way faster. The arrangement of charges totally changes the shape of the map.
So far, we've been talking about charges in a vacuum. But what happens when these energy maps run into actual real-world materials, like a chunk of metal? Well, this is where things get really practical.
Okay, so when you put a conductor, like metal, into an electric field, something amazing happens. The free-flowing charges inside it instantly shift around until they completely cancel out the field inside the conductor. They basically create a perfectly calm, zero-field zone internally. Because of this, any extra charge you put on it gets pushed to the very outer surface. And this leads to a wild consequence. The entire object, every single point on it and in it, sits at the exact same voltage. It becomes what's called an equipotential surface.
And that self-canceling behavior creates this incredibly powerful effect, electrostatic shielding. It means if you have any hollow space inside a conductor, that space becomes a perfect safe zone from any electric fields outside. You could have a massive lightning storm raging all around you, but inside that cavity, it would be perfectly calm and field-free. This is exactly how a Faraday cage works.
All right, so we can map these energy fields, and we can shield ourselves from them. But what if we want to grab that energy and store it on purpose? That brings us to our final topic, the capacitor. And here it is, the capacitor. At its heart, it's a really simple device. It's just two conductors separated by an insulator, like air or plastic. Its whole job is to create a space where we can intentionally build up potential energy. We apply a voltage, which separates positive and negative charges onto the two plates, and we store energy in the electric field that builds up between them.
Now, how good a capacitor is at its job is measured by its capacitance. We call it C. It's just a simple ratio. How much charge can it store for every volt of potential difference you apply? So a high capacitance means you can cram a ton of charge onto it without needing a super high voltage. And that value is all about the physical shape of the capacitor, how big the plates are, what they're made of, and how close they are.
So here's the bottom line. A device with a really big capacitance is incredibly effective. It can hold a massive amount of charge and energy without needing a dangerously high voltage to do it. And that's absolutely essential for pretty much all electronics, making capacitors a key player in everything from your smartphone to the entire power grid.
So think about where we've been. We started with the raw, chaotic energy of a lightning bolt and ended up with a detailed map of the invisible world of electrostatic potential. We've learned how to build shields to protect ourselves from it and how to build devices to capture and store it. We now have the fundamental tools to control one of the most powerful forces in nature. So the only question left is, what are we going to build with it?